So the given problem here, it is said that using bilinear transform method, derive h of z for the analog transfer function h of s with the resonant or otherwise the cutoff frequency omega r equal to pi by 2, where h of s is equal to s plus 0.1 s plus 0.1 whole squared plus 16. Okay, go to the solution. So as per the definition of bilinear transform, we can simply write h of s will be equal to h of z if and only if s is equal to 2t over 1 minus z inverse by 1 plus z inverse. Simply in h of z, or in h of s, if we replace the value s with this quantity, we will end up with h of z. So generally speaking, the transfer function of an analog filter which is given in the form, so generally if h of s is having a form s plus a divided by s plus a whole squared plus omega c squared, then this omega c is the cutoff frequency. Mind it, it is the cutoff frequency of the desired filter in linear fashion. This omega r is an angular frequency that is completely different from omega c squared. So from this we can easily find out omega c comparing this expression with this one. Omega c will be equal to root over 16, that is equal to 4. So now we get the cutoff frequency of the analog filter, and we have the cutoff frequency of the demanded digital filter, omega r. So what we need to do is get this value of t. So in order to get the value of t, in order to quantify t, we can use the expression omega is equal to 2 over t tan of omega 2. So from here we can find out t is equal to 2 over omega tan of omega over 2 is equal to 2 over 4 tan of pi by 4, which is equal to 1/2 seconds. Now we simply find out h of z, which is equal to h of s, where s is equal to 2t z inverse by 1 plus z inverse. In our case, z will be equal to s plus 0.1 -1 2 over t z inverse 1 plus z inverse. Plug in the value, we get 4 into 1 minus z inverse divided by 1 plus z inverse 0.1, which is divided by 4 times 1 minus z inverse by 1 plus z inverse 0.1 squared plus 16. Simplifying a bit further, add these two expressions up. This will become 4 1 minus z inverse 0.1 1 plus z inverse divided by plus z inverse, and this will be 4 1 minus z inverse 0.1 z inverse whole squared 16 by 1 plus z inverse squared. One further simplification, we can write minus z inverse z inverse times 1 z inverse squared plus 16. Just simply cancelling this term with the square, and this term will go up to the numerator. So the rest of the calculation I think you can do by yourself, so I will go finally to the result. It will be 1.28 z squared plus 0.006 z 122 by z squared 6 z 0.975. This is our required transfer function of the digital filter. So we complete our filter designing using bilinear transform.